Electric charge and electrostatic force. These are from chapter number 21, page number 609. The topics include electrostatic charge, how the charge interact with other charges, electrostatic force, Coulomb's law in scalar form, and Coulomb's law in vector form. Let me first start from the electrostatic charges. But before I'm going into detail about the electrostatic charge, its properties, its attraction, how the charge produce force, how the charge produce electrostatic field, let me give you a few examples from the daily life so that one can understand how the charge produced over any surfaces, or what is the procedure to incorporate the charge over any surfaces. I hope everybody has experience that especially in winter session or dry weather, when you pass a plastic comb through your hair, you will find the comb can exert a force on individual strands of your hair. You may also observe that once the strands of your hair are attracted to the comb and come into the contact with it, they may no longer be attracted to it. Well, it seems reasonable to conclude that the attraction between the comb and hair is a result of some physical entities being transferred from one to other when they rub together. When the same physical entity is being transferred back again to the neutralize the attraction when they come into the contact. This physical entity is called electrical charge. And we're lucky enough today we understand this transfer on the basis of electrons that can be removed from the atom of one object and attached to the atom of the other object. Therefore, in this case, your comb has a negative charge because it receives excessive amount of electron from your hair, and your hair become a positive charge because most of the electron moves to or transferred to the comb. Therefore, there would be some electrostatic interaction introduced because of the different polarity of the charges. Let me give you another example. When we rub a plastic rod with fur, electrons are transferred to the rod. Because it has an excess of electron, the rod becomes negatively charged, and consequently the fur now has a deficiency of electron, and so it is positively charged. So now let me come up to the properties of the charges. The charge is a basic property of matter, just like a mass and energy of the material. Human cannot directly sense the charge, but some animals can sense it very easily. We can observe charge indirectly via its effect on matter. And symbolically, sometimes represent small q, and sometimes it represents capital Q. Depending upon your comfort, you can use it what you want. And as a charge is a measurable quantity, therefore this must have a dimension. So the charge measured in Coulomb, which represent capital C. As I mentioned before, that the charge has two kinds. One is positive and other is the negative. Therefore, their interaction also must have two kinds. Like charges repel each other and unlike charges attract each other. And these interaction can be more clearly understood by the following picture. If two charged particles, either positive or negative are brought near each other, they each exert an electrostatic force on the other. The diagram of the force vector depends on the sign of the charges. If the particles have the same sign, like positive and negative, they repel each other. That means that the force vector on each is directly away from the other particle. If you release the particle, they accelerate away from each other. If instead we have particle have opposite sign, like in this case either positive or negative, they attract to each other. That means that the force vector on each is directly towards the each other. And if you release the particle to free from this point, they accelerate toward each other. Similar as the law of conservation of energy and law of conservation of mass, the charge is also follow the conservation law. Net amount of charge does not change in any process, each having an absolute value of 1.6 10 to the power minus 19 Coulomb. And this is the smallest value of the charge appear on any entities. Therefore, electron is the smallest particle of an atom. Therefore, this number is associated with electron. A neutral particle known as neutron. And in order to balance these positive charge, a negative charge is revolving around this nucleus, so that the whole atom is considered as a neutral atom. Now let me introduce some negative charge around this nucleus. One electron is here, 2, 3, 4, 5, and 6. So 6 electron is around the nucleus and 6 proton is within the nucleus. Therefore, the whole atom is considered as a neutral atom because number of electron is equal to the number of proton. Now let's see the second scenario. Let me add 2 more electron to this atom. One electron added here and another electron added to here, so that we have the total number of electron is now being 8, which is greater than the number of proton available to this nucleus, which is 6. Therefore, this atom is considered as a negative atom because number of electron is greater than the number of protons. And now third scenario, let me first remove the added electron from this atom, and this was also added to this atom, and now we have a neutral atom because 6 electron is revolving around this orbit and 6 proton is available to the nucleus. Now let me remove more electron from these surfaces. So let me remove one electron from here and another from here. So now we have 4 electron around the nucleus and 6 proton is available to this nucleus. Therefore, this atom is considered as a positive atom because the number of electron is smaller than the number of proton. Coulomb's law. So in order to find the strength of the electrostatic force, the magnitude of the electrostatic force, Coulomb found that the electric force between the two charged objects is proportional to the product of the charges on the object, of course charge object, and inversely proportional to the square of the separation between the charge object. And mathematically we can write force is equal to constant Q1 and Q2 divided by R square, where K is the constant of proportionality, has a value of 9 into 10 raised to the power 9 Newton meter square per Coulomb square, which is also equivalent to 1 over 4 pi epsilon naught, where epsilon naught has a value of 8.85 into 10 raised to the power minus 12 Coulomb square per Newton meter square. Keep in mind that epsilon naught is called the permittivity of the free space. That means if nothing is present between the charges, or we call it the vacuum between two charges, we use this number. And however, if we place some insulating medium or some liquid between the charges, then of course this epsilon naught is being changed accordingly, and of course this number would also be changed. Therefore the force depends on the medium as well. As with all forces, electric force is a vector quantity, so we must careful to find the direction of the force as well. F vector is equals to K Q1 and Q2 divided by R square R cap, where R cap is a unit vector pointing from Q1 to Q2. The direction of the force is either parallel or anti-parallel to this unit vector depending upon the relative sign of the charges. Let me show you one example. Sorry. Two charges are separated by a distance r and have a force F on each other. According to the Coulomb's law, this force can be determined through these equations. If Q1 and Q2 are known and the distance between two charges are also known, then we can find the force by using these equations. Now it is better you just pause this video and answer it. For example, if R is double than F, therefore then initial force would be 1/4 of the F. And if Q1 is double, for example, you just replace Q1 to twice of Q1, then of course initial force would be twice of the initial force. And if Q1 and Q2 are double, mean here both become twice, and R is half, so this R would be replaced with half of the R. Then what happens with the initial F? Then the answer would be the initial F would be 16th time of the F. Now the force acting on each charged object has the same magnitude but acting in opposite direction, and this is according to the Newton's third law. Previously we have seen that the Coulomb law only gives the idea to find out the force between the two charges. Now if we have a number of charges, means more than two charges. Look at here, three configuration of the charges Q, Q1 and Q2. If you need to find the charge, if you need to find the force from Q1 to Q and Q2 to Q. So there are two kind of force because both have different magnitude and different directions. As I have mentioned before that the electric force is a vector quantity. So in order to find the force between these two charges Q1 and Q and Q2 and Q, we must careful both to the magnitude and direction as well. So what we do here, first you need to find the force between these two charges, and then we need to find the force between these two charges, and then we need to add up both charges. So the idea to add up both of these charges is to use the superposition principle, and superposition principle is nothing but the vector addition of these forces, and the net forces would be somewhere in this direction that can be determined through vector algebra. So finally, we studied the Coulomb's law, but keep in mind this is our official starting equations, and also we call it the fundamental equations. So we don't need to drive anywhere from fundamental point. This is our fundamental equation. So whenever we need this equation, you can start from here. You don't need to start somewhere else. And the other important point is that there could be freedom to use either small q's or capital Q's. Distance could be represented either from R or D. Force could be represented as F12 or Fe. I mean, this is all up to you, whatever you want, but keep in mind meaning of the corresponding terms would not be changed by any way. Now let's compare two forces. Electrical force or electrostatic force we have already studied in previous slides, that can be determined through the Coulomb's law. And if you recall, another forces we have discussed in previous lecture, we call it the gravitational force. So now if I ask which force is strong enough, either electric force or gravitational force, so your answer would be based on some short numerical problem. If you look at here, two 40-gram masses, each with a charge of 3 microcoulombs, are placed 50 centimeters apart. Compare the gravitational force between the two masses to the electric force. Ignore the force of the earth on the two masses. 40 gram having a distance between them is 50 centimeter, and two charges have 3 microcoulomb having a distance is 50 centimeter, and the microcoulomb means 10 raised to the power minus 6 coulomb. So in order to find the gravitational force between two charges, you just write the gravitational equation m1 m2 over r square, incorporate number, but keep in mind number would be a same unit, either meter or centimeter or whatever you want, and the answer would be 4.27 10 raised to the power minus 13 Newton. And if we find the electrostatic force between two charges separated by 50 centimeter apart, then after incorporating the numbers you will get 0.324 Newton. So if we compare both numbers, you will find that the electric force is much greater than the gravitational force. Let's have a look another problem based on a superposition principle. In this problem, we have three charges of different magnitudes placed at a different positions on xy plane, and we need to find a force on one charge due to other two charges. Problem statement is given here. A positive charge Q1 has a magnitude of plus Q, is located a distance d along the y-axis from the origin. A second positive charge again have a magnitude plus Q, is located at the origin, and a negative charge Q3 has a magnitude of minus 2Q, is located on the x-axis a distance 2d away from Q1. So the distance between Q1 and Q3 is given as a 2d. Calculate the net electrostatic force on Q1 due to other two charges Q2 and Q3. Before I'm going to solve this problem, let me recall few points which really important in such problem. For example, in such problem where we have a configuration of charges, then we need to define a coordinate axis because this is two-dimensional problem. Therefore, let me draw xy plane. For example, a vertical axis and a horizontal axis. Vertical axis on the top is defined as plus y. Vertical axis in the downward we define as minus y. Horizontal axis on the right side, let me define x-axis, and horizontal axis on the left side, let me define minus x-axis. And second point is force vector. Let me define a positive charge placed at here and another positive charge placed somewhere at this point. Distance between these two charges, say r. So, and we already know that if you have a same sign of charges, then the force is repulsive and the force vector is away from the line joining of these 2 points in both cases. However, if we have two opposite sign of polarity, say a positive charge and a negative charge, distance between these two charges again consider as r. In this case, because of the opposite polarity, the force would be an attractive and the force vector would be towards each other in both cases. The third and last point is if we have a vector or xy plane, let's say we call it, this is a vector of A making an angle theta with respect to the x-axis, and in order to define its component, because this vector is located on xy plane, neither it parallel to the x-axis nor it parallel to the y-axis, then this vector must be resolved in its component. And what would be the two components of this vector? Let me draw here. This is a one component, which is vertical component, and another is the horizontal component. Vertical component is called, this is the AY, and horizontal component represented as AX. Okay, now let's move to solve this problem. Let me place the given charges on its location. Q1 is given in problem from origin to a distance d above the y-axis. So I have placed Q1 here, and Q2 is placed at origin. So this is origin, and now this is horizontal axis, we call it x-axis. So the third charge Q3 is to be placed at x-axis from the distance 2d. So these are the three charges, Q1, Q2, and Q3. As per given problem, we need to find a force on this Q1 because of Q2 and Q3. So in order to solve this problem, we need to find the force between Q1 and Q2 and force between Q1 and Q3, and then finally we have to add both these forces vectorially, and then we will get our final results. So, but before I'm going to find the magnitude between the force of Q1 and Q2, Q1 and Q3, let me first define the direction of both forces between Q1 and Q2 and Q1 and Q3. If you look at here, this is a positive charge, and again Q2 is a positive charge, and because the same charges repel to each other, then the force from Q2 to Q1 would be repulsive. Then the direction of the force would be from this point to upward along the y-axis, and that can define as this vector. Let me call this vector is F2. And if you look at here, this is a plus charge and Q3 is a minus 2Q. Then the force from this Q3 on Q1 would be an attractive force, and the direction of the force towards each other when we have an opposite charges. So F3 must be in this direction along the line joining of these 2 points. So we need to find F2 and F3. Therefore, the net force can be written as F2 plus F3. Now let me find these two forces one by one. So F2 is equal to K Q1 and Q2 divided by R12, and R12 is the distance between Q1 and Q2, and Q1 and Q2 is actually given here. So let me substitute this value in this equation. K, Q1, Q2, and divided by D square. So you just multiply these Q's, you will have Q square divided by D square, and J is just the representation of the unit vector, that the vector is along positive y direction. This is our force between these two charges. Now let me determine the second force, which is F3. But keep in mind that F3 neither parallel to the x-axis nor parallel to the y-axis. Therefore, we have to resolve in its component. Therefore, first component would be along the positive x-axis and other component along the downward direction, which is the negative x-axis, by the way, where angle is given somewhere theta. So in order to find F3, we first write F3 into its component. As I mentioned here, that F3 has two components. One is a horizontal component or x component, and F3y is a vertical component. Let me substitute the components form. F3 is equals to F3 cos theta I. I again is a horizontal component unit vector, minus F3 sine theta j. J is a vertical component, but keep in mind this negative sign is incorporated here because the vertical component is downward direction. Initially we have defined that the vertical component upward is considered as positive. Consequently, the downward vector will be taken as negative vector. So this is the F3 F3 vector, F3 cos theta I cap minus F3 sine theta j cap. So in this case, we need to find F3, which is the magnitude of the force between Q1 and Q3, that can easily be determined through the Coulomb's law. However, cos theta and sine theta can also be determined through these triangle, because you already know that the sine theta is equals to half and cos theta is equals to root 3 by 2. By just all of this number was taken through this triangle, and F3 can be written as Q1 and Q3 divided by R13 square, Q1 and Q3 divided by R13 square. Let me substitute the values of Q1 and Q3 along with the sine theta and cosine theta in this equation. So these are the values substituted to this equation, and finally when we solve these equations, we get a two component of F3. This is a horizontal component and this is a vertical component. So now we have determined F2, which has only one component, and F3, which has two component. One is a horizontal component and other is a vertical component. Let me add both vector F2 and F3, and then we'll get the force on Q1 due to these two charges Q2 and Q3. I mean, this is just addition algebra. You can just add up vectorially, and finally we will have a force, of course, has the two components, x component and y component. So this is our final results. Important point is that although I have given every steps in solution, but you don't need to do step by step. Once we have become an expert of a problem like this, you can combine and perhaps even skip some steps. Skipping steps on work to be graded is not recommended in this case. You may express your answer in unit vector as on the previous slide, and you may also express your answer as a magnitude and direction as well. So Amit, this is up to you. Example number 3. This is another problem that helps to uh, understand the superposition principle. The problem is somehow same as the previous example number 2, but there is a little difference, and the difference is in this problem we will have exact number of the corresponding charges. Problem is 3 charges objects are placed as shown in the given figure. Find the net force on the charge of minus 4 microcoulomb due to plus 5 microcoulomb and minus 5 microcoulomb. And the placement of these charges is given in this problem. You can see here we have a 3 combination of charges. Plus 5 microcoulomb is placed at origin. Minus 5 microcoulomb is placed on a vertical axis from 20 centimeter apart from the origin, and minus 4 microcoulomb is of 20 centimeter apart from the origin on x-axis. Therefore, as per given problem, that we need to find net force on minus 4 microcoulomb. This is the charge where we need to find a force from these 2 charges. So let me first draw a line or the force vector between Q2 and Q and Q1 and Q. 20 centimeter is the distance between these 2 charges, and 20 centimeter is the distance between these 2 charges, and because this is the right angle triangle, so this side can be determined through the Pythagoras theorem. You will get 28 centimeter. If you need to find the force as well as the direction in all cases, let me draw a direction of the force between these 2 charges. So as you know before that if you have 2 opposite charges, then there must be an attractive force. Therefore, direction of force on this Q because of this Q1 is in this direction. Direction of the force and the force from Q2 to Q in this direction, because of the same sign there must be repulsive force, and the force vector is away from this line joining the 2 charges. So we need to find these 2 forces, and in order to find the total force we just add up vectorially F1 and F2. Okay, now let's determine one by one. This is the Coulomb's law, and first let me find F1. Of course F1 has only one component because this is along the x-axis. F1 can be written as this is the value of K, Q1, Q2 divided by the distance, square of the distance between 2 charges, and you will have a magnitude 4.5 Newton. between Q1 and Q. And the force between Q2 and Q can be written as 2.3 Newton by just incorporating all of this number. But keep in mind that this vector neither parallel to the x-axis nor parallel to the y-axis. Therefore, we have to resolve in its component. This vector must have two components, x component and y components. These values of f1 and f2 have been determined in previous slides. Let's plot these values. As given in the previous slide, f1 is along the negative x-axis and f2 is on the plane of positive x-axis and negative y-axis, making an angle 45 with respect to the positive x-axis. Their values are given here, which have been determined previously. And as I mentioned before, that f2 must be resolved in its components. So let me resolve it. So one component of f2 is along the positive x-axis, which is the horizontal component, and another is along the negative y-axis, which is called a vertical component. And the horizontal component can be determined through the cosine law, which is 2.3 cos 45, and the vertical component can be determined as 2.3 sine of 45, which will be 1.6. So let me write these values in terms of a vector notation. So f1 is equals to minus 4.5 I cap. I cap is the representation of unit vector along x-axis. So the minus sign is coming here because of this f1 is along the negative x-axis, and no vertical component is exist in f1, so we just put 0 j cap. And f2 is equals to plus 1.6 I cap minus 1.6 j cap, where minus sign appears here because of the vertical component is in the downward direction. And now we need to add both vectors. So the net vector is equals to minus 2.9 I cap and minus 1.6 j cap. So this is the resultant of these two vector f1 and f2. Let me draw this vector in this coordinate, minus 2.9 iota cap. Minus means this must be along the negative x-axis, and minus 1.6 j cap, that means this must be along the negative y-axis, and the resultant of this two vectors can be drawn through the head to tail rule, and mathematically this can be determined through this method, so which will be 3.31 Newton. And the angle can also be determined through the tangent law, which will be 29 degree. And in general, this angle is measured with respect to the positive x-axis. So in order to measure from positive x-axis, we just need to add 29 plus 180. That will be 209. Thank you.